Hello student, this is your instructor Dr. Aijaz. I will be teaching you General Physics 1 course. This course is based on the mechanics. We will cover kinematics, forces, energies, rotation, motion as a part of this course. The primary method of instruction for this course is the Blackboard instruction. However, in some of my videos, you will see me going over the PowerPoint lectures. But most of the lectures, they are Blackboard based. We will do our first chapter today, which covers the physical quantities, measurements, and the estimation process and uncertainties involved in any measurement. But first of all, how do we define physics, and which area of science physics usually covers? Physics covers the matter and its interaction with the surrounding. Phenomena like where the objects are not being changed chemically and only they go through the physical changes, those fall into the category of study of the processes involved in physics. For example, if you are driving the car in the morning to come to school, that car motion, the wheels are rolling, the car is moving in a straight line. If you turn to the right or left, physics is involved, and we study those kind of motion under kinematics. Then there is a force on the car too. We know that there will be frictional forces. There is an engine force on the car which is pulling it forward. Frictional forces are acting opposite to the actual forces. So all these forces are acting on that car. That is the part of physics. So we will be working with the several phenomena involved in our everyday life which are related to physics. Basically, you will be surprised to see there are so many things that we do and we don't realize that there are so many physics principles which are playing a role in that. Like all other sciences, physics also starts with the observation. Observations are made, hypotheses are made, and as a result, we come up with the laws, principles, and theories. Example of the law is the Newton's second law. So law is mostly a form of a statement and it can come with a mathematical form. And theories, they are more elaborated. It has multiple points like Bohr's atomic theory, which talks about how the atom is composed of the nucleus and the electrons, where the nucleus is situated at the center and the electrons are revolving the nucleus. So those kind of things which need more detail, they are given in the part of theory. It doesn't mean that theory is any less valid than the law. It is equally valid. However, it is just given in different postulates. And then principle, which is less general. For example, one example that you will probably learn during this course too, Archimedes principle. Archimedes principle is only for fluids, fluids like gases or the liquids, and it's not for every matter. It's mostly for fluids. So that is it's defined as the Archimedes principle. Since I mentioned the observations, so what kind of observation are we making? There are physical quantities involved which require measurements, and there are 7 fundamental physical quantities that are taught in physics, and we will be using 3 out of 7, and that is the length, or distance, mass, and time. These are the 3 fundamental quantities which will be used, and all other quantities that we will learn, which are new physical quantities, they can be derived from these 3 quantities. For example, everybody is familiar with the speed, how fast we are going on the road. And you see 55 miles per hour or posted on the road, and these values, the speed, the basic definition of speed is the total distance over time. So you could see that this speed is a quantity which tells you how much distance you have covered. Like if you go for an hour with the same speed, you will cover 55 miles. That's 55 miles per hour. Total distance covered over total time. So it includes two fundamental quantities, distance and time. So all these quantities are called derived quantities, and they can be defined. We should be able to define them in terms of these three basic physical quantities. And it's also very helpful in getting the relationship between different quantities. That is called the dimensional analysis. Like for the so in dimensional analysis, L is used for distances and length. M is used for mass. T is used for the time. And we can use these quantities in order to see or check if the equation is correct. For example, we know that area is the length multiplied by so for the dimensional analysis for area, we should get L times L equal to L square. Okay, and that should be correct because it is related to the two lengths of the side. We can do the same study for the volume as well. For speed, the dimensional analysis will yield L over T, right? L is for the distance, T is for the time. Now, these are two quantities where we are not really checking any equation here. However, we can use some equations where we can actually check if that equation is dimensionally correct or not. For example, you drop an object and that object is dropped from a certain height, and that object has landed on the floor, which is about h meters high above the floor. Now this dropped object should have the value of dependence on different quantities. Now if I ask you, you may tell me, okay, as you increase the height, it's going to take more time to reach the ground. Yes, that is true. So probably the height has some sort of dependence on let's say t square, okay, and you increase the height, you increase the time, the height would increase more. So, like it is proportional to the square of t. Now, what else could be the part of it? Maybe the velocity or speed at which it is falling, or maybe the rate at which the velocity is changing, or because we know the things speed up as they approach the ground, as they get closer to the earth. So if we put the v here and we want to see if this equation is something that could be true for the dependence of height on time, and so we check it dimensionally. So h is represented as L, v is L over t. V is same as speed and velocity. Unit wise they should be the same. And this one is t square, 1t gets cancelled, you will have L over T. Now look at the right hand side and the left hand side, they both are different. So dimensionally this equation is not correct. Now from the experimentation, we already know what really affects the height of any objects reaching the ground, that is equal to another quantity which involves the change in velocity. Like we define the speed as the distance covered over time, we can also define delta V over time, change in velocity over time. That means it is like L over T divided by T, L over T square. That is the dimension of the quantity. If you notice, if I plug in instead of V, if I plug in T square here, T square would get cancelled and I would get only the dimension of length, which is dimensional. So this equation will be dimensionally correct. Now this equation doesn't give me the whole story because I already know that should be a constant factor here, which is omitted because the numbers do not have the dimension. So constants, that is something that you cannot find using the dimensional analysis. That is only true for finding the dependence of the quantities on each other and coming up with the equations. So this is a very useful analysis for finding the dependence or relationship between different quantities. Now these three quantities, they can be represented dimensionally using L, M, and T, but if I tell you to get up and walk 5, I'll give you a number 5 and tell you, okay, go do 5. You're going to ask me, do 5 what? So we always define everything in terms of a set of units. In physics, we are using System International or SI units. As a part of the SI units, length is always measured in meters or m. Mass is always measured in kilograms, not grams, kg. And time is measured in seconds, s. So these are the set of units that we will always do our work in. This one is also called metric system or MKS. MKS, M stands for meter, K stands for kilogram, S stands for second. There is a smaller metric system too, where you could use centimeter for length, you could use gram for the mass, and you can use the second for the time. That's called the CGS system. But I would always tell you to use this set of units. So whenever you see your numbers given in centimeters or grams, you would convert them to MKS system, convert centimeters to meter, gram to kilograms, and seconds. Second remain the same for both. And there is also an equivalent British system which is used to represent the same quantities, which we use a lot in our everyday life. For the length, we use, I'm going to write that on this side, British system, foot for, that is linked to the human foot for the length, pound for the mass, and second for the time again. So second remains the same always. This can be also abbreviated as FPS system, but this is used a lot in our everyday life. We talk about the heights, our heights in feet all the time. We talk about the weight in pounds. This one is in fact the unit of the weight. However, it is given. It is used as a part of the FPS system here. So we will in our calculation, in our problems, I would always tell you to do your conversion. And there is a reason. Sometimes it's okay to work with the same set of units. However, when the constants are defined and you use those constants with the defined numerical value and different set of different unit into your calculation may go wrong. For example, if you are using, there is a quantity which we will learn, g is the acceleration due to gravity. This is the given value in meter per second square. So we use it very often for solving a problem when we deal with a free falling object. So when you use this value, you will have to convert your distances to meter, and your time should be given in second in order to be to use the same equation for both. All right. So when we make the measurement of these quantities, are they always correct? They could be, and there could be uncertainties involved in them. All measurements have uncertainties. How do we take care of them? Use better equipment. For example, I have an example of the meter stick. Now, this meter stick is marked as 100 centimeter, and the least count for a meter stick that means the minimum value a meter stick can measure is 1 millimeter or 0.1 centimeter or 1 millimeter. That's 1 meter stick. Now if I take a small ball here and I make a measurement here, and what I see here, so if I try to be very accurate and put something on the ends and take the reading, I am getting 2.5. It's the diameter of the ball and 2.5 centimeter. If I ask you, you're going to tell me, I cannot see. I can see it's roughly on the fifth division. However, I cannot see if it's little behind 5, if it's little ahead 5. I cannot see that because it's not marked on there. You're going to see 2.6 next. You can't see what's between 5 and 6 because it's not further divided. So if I could use a better equipment or better instrument in order to measure it, for example, I have a vernier caliper here. Now, vernier caliper has the least count of 0.01 centimeters. So further, you can go one more digit to the right in order to get more accurate answer or closer number to figure out it was little over 2.5, but what it really was. You can reveal that answer using the vernier caliper. So here, if I ask you the uncertainty, you're going to tell me, oh, maybe it's plus minus 0.1. That's a reasonable answer for this measurement. You could go above 1 and below because you cannot be too wrong. We can see that if different people can make the same measurements and get some uncertainties. From there, you can get a better number or accurate answer there. This one, however, if I put the same ball here between the jaws of this vernier caliper, if I place this in here and close it, okay, what I see is it is at 2.5, but it's little ahead of 2.5, and that is but there is a method of making the measurements. There are two scales here. So what I see here is 3, this scale, and then there is a scale on the top of it which is moving. Let me do that with a different color. This scale is somewhere here. The first division of that scale is here, and then there are 10 divisions. There are 10 divisions. So each millimeter is further divided into 10. So we have the now the method for finding such values is the we have to see which division is exactly in the same line with the linear scale, and that is, for me, it's 3. 3 is multiplied with the least count and it's added to it. So the total measurement become 2.53 centimeter. Now it's more accurate. It's more reliable because you have the you have about 2 digits value for this sphere. However, now the uncertainty, we cannot say it's completely accurate. Uncertainty will still be there, and roughly we can estimate it as maybe this time it's plus minus 0.01. The last digit maybe not so sure, because here the way we measure it, maybe for me it is the third division which is overlapping with this linear scale. Maybe if I ask someone else in the class to check, they can check. So the uncertainty will be defined in a different way. This is when we define these uncertainty. Sometimes these are assumed uncertainties. Sometimes these are the estimated uncertainty. The best way would be to get the data and figure out the average value of that data and calculate the plus minus maximum or the minimum value it can reach to. That would be your estimated uncertainty. How do we take care of the uncertainty in our measurements? If you are multiplying two numbers, you will have to go with the, for example, if you have, let me take some example here, some real numbers. 11.3 times 6.8. Now, if you use the calculator, the answer would be 76.84. Where you should stop. Here, there is something which is called the significant figure, number of significant figure, which becomes very useful. How many numbers I should keep here in order to have an accurate calculation. I will have now this one has the 2 significant figures, and this one has 3. Now we have to go with the minimum number of significant figures to keep our answer as accurate as possible. So in this case, this would be, we should keep 2 significant figures because they are being multiplied. So the actual answer would be 77. If this is in centimeter, this becomes centimeter square. All right. So that way we could keep the uncertainty, and so significant figures, keeping track of significant figures is a way to reduce the uncertainty in your answers or error in the answer numerically. So if these are not being multiplied, instead of that they are being added, then you have to keep with the small number of accurate figure. For example, you have 0.57 and you add plus 3.6. So you are adding them. So this rule applies to both adding and subtracting for both. So if you add them, you will get a number 3.03. Now, this one has how many significant figures it has? It is known up to, so there are 2 digits known from the decimal point. And here you have about 1 digit known of the decimal point. So we have to go, which one is the least accurate one? 3.6 is the least accurate one. So we have to go with that. So this becomes 3.03. Now, why did I put the 3.03 there? why there is there anything I needed to do? Yes, here the rounding off plays a role. If this number is equal to and greater than 5, this will be rounded off. So when we are using the significant figures and where we stop our numbers, we have to see the next number if it is equal, and so here we don't need to round here. This is a concept which is introduced at elementary level, and I think everybody should be familiar with that where we have to round it off and in order to keep the required number of significant figure in our answers. Also, we will be working with the unit conversions, and for that in your book all the conversion factors are given. If you have a different method of conversion, but as long as you follow the correct conversion figures, you should end up with the correct answers. So I would just go over one example of the unit conversion here. And for example, if you have, if we are covering 55 kilometer per hour, and like I said, we prefer to keep our calculations in the MKS format, and if I convert for that, I will have to convert this to meter and this to seconds. So in order to do that, I first have to figure out how many meters are in 1 kilometer, so or the conversion factor. So I will take the conversion factor for 1 kilometer equal to 1000 meter, and 1 kilometer over 1000 is equal to 1, and I do the same for hour. So 1 hour is equal to 6, so 1 hour is equal to 60 minutes, each minute 60 seconds, 60 times 60 is 3600 seconds. So I know that this is a conversion factor equal to 1. So I do have two conversion factors which I can use in order to convert the 55 kilometer per hour to the meter per second. So 55 times for kilometer, I have to plug in 1000 meter over 1 kilometer. Okay, so I have inverted it because this is how it should go in there. Divided by, for hour, I can replace it also by the same 3600. So there is hour in the denominator. Multiply by 3600 seconds over 1 hour. I did the same thing here. I just so you can write this as 3600 seconds over 1 hour equal to 1. It's the same thing. So we can use that here. Hour gets cancelled, kilometer gets cancelled. So the key is you have to invert these values such way that this one, the unit should be in the denominator, so it gets cancelled out. So kilometer is cancelled out, 1000 is there, and 3600 is there. So remaining value will be equal to 55 times 1000 divided by 3600. Cancel out, and when I take a calculator, multiply them, I get let's see, 15.3 meter per second. So by using the conversion factor, I could convert the numbers given in any units into the required units. sometimes the uncertainties are really high in the numbers, and we merely use some sort of estimation to get some idea about maybe a bigger version of something. For example, if you are building a very large rectangular plate, and you can estimate how many plates will make that one large plate, and you can estimate it by adding their areas together and figure out the overall required area for the bigger plate. So in order to get the idea about huge numbers, like how many times cells are in human body, how many steps have we taken in last 4 years. So if when we are doing the estimations like that, in those cases we tend to round it off to one significant figure and use the power of 10. For example, if you have mass, if there is a limitation that you cannot use the estimation, then this is not how it is done. Then you would take the 82 kilogram. But if the estimation is allowed and you just want to estimate to the closer number, this would be, you can use it to 100 kg, which is 10 to the approximately equal to 10 to the 2. So you can write it in the form of the one significant figure followed by the power of 10. We could do, this is not very useful here because 82 kilograms is it's a reasonable number. However, when we are dealing with very long distances and something we don't have a very good idea about, something is not very symmetric, you are, for example, you are trying to get the amount of water in the pond of water, in a pond, and you may think of a pond as a cylindrical object, and you can figure out the volume of it and then figure out how much volume it would be carrying inside of it. So those where we are not very sure about the symmetry and the numbers are very huge or very small, then the power of 10 could be very handy. Let's do one example where we are going to estimate the number of cells in the human brain. Now if you Google this, that what is the size of the brain or head, it should be about 20 centimeter. So I'm looking at the scale right now, and I would see that 20 centimeters should be a very reasonable number for the length or the size of the brain. So if we could estimate the size of the brain or volume of the brain, then we can also try to estimate the size of a cell. If we could do that, we can easily see how many cells can accommodate in that volume to make it up. All right. So this is our strategy of going about this problem of estimation, that if we know the whole volume of the head or the brain, and then we figure out the approximation of the size of a cell, we can figure out how many cells can get in there. So using this 20 centimeters, so the length of the brain is, so I'm going to estimate the volume of the brain. Now volume is nearly spherical. I should use the 4/3 pi r cube, but this is not going to make too much difference because we are working with estimated numbers. So if I just take L cube for the volume, and I take 0.2 centimeter, convert it to meter, that becomes, 0.2 meter, and then I take the cube of it, it's going to give me about 8 times 10 to the negative 3 meter cube. Now, since we are already estimating the numbers, it is okay to estimate it close to 10, and 10 times 10 to the negative 3 meter cube, that becomes 10 to the negative 2 meter cube. Roughly, the volume of the human brain is going to be this much, V brain. And now we need to estimate the size of the cell. Now there are different sizes that you can find over the internet. I am using the size approximately equal to 10 micrometer. I'm going to erase it. So V cell, or let's use the same for the size of the cell. So I'm using the size of cell approximately equal to 10 micrometer. So 10 micrometer means 10 to the negative 6. 10 cube negative 18, that gives me negative 15 meter cube. Okay, so we have volume of the brain, which is, let me rewrite the volume of the brain here. Volume of the brain is approximately equal to, what was that, 10 to the negative 2 meter cube. And we have also, to me they look very reasonable, because the cell size is considered is of the order of magnitude of 1 angstrom. So when we have this number, it looks smaller than that, and the brain size also looks very reasonable. So in order to get the number of cells, we can divide the total V brain divided by V cell, and that would give me 10 to the negative 2 divided by 10 to the negative 15, both in meter cube. Can cancel, because we are working for the numbers. Numbers should not have any units at the end. We are going to get a number like 10 to the ten to the 13. Okay, this many cells. It's a big number. Yes, it does seems reasonable estimation of the number of cells present in the head. This method can be used in order to find out bigger volumes, bigger areas, or unsymmetrical shapes which are similar to some known shape, in order to get the volumes or areas. I'm going to stop here.